By the end of this video, you should be able to predict the solubility of an ionic compound or a covalent molecule. You will need your solubility video worksheet and a pencil. For any substance to dissolve into a substance, a three-step process must occur. Now, another name for the substance that's being dissolved is a solute. Whatever it dissolves into is a solvent. So let's talk about this three-step process. First, there's attractive forces that hold the solvent together. They have to be broken. Next, there's attractive forces that hold the solute together. They have to be broken. Once they're broken apart, the solvent and the solute can come together. And when they do, an attractive force from the solvent to the solute must be formed. Let's get some examples of this in action. Our first problem is methanol in water. Methanol is CH3OH. It would look like a C with 3 H's, then bonded to an oxygen and another H. This is a polar molecule and it's able to do hydrogen bonding. So what are our three steps? First, the solvent, which in this case is the water, needs to break up its attractive forces. So we can see here all these dotted lines. Those attractive forces between the water molecules must be broken. This will give space for the solute to get in between. Our solute is methanol. The methanol also has attractive forces. Remember, it is a polar molecule that's eligible to do hydrogen bonding. So we're seeing these dotted lines here. These are the hydrogen bonding attractive forces between methanol molecules. They also have to break up. When they break up, it allows the methanol to get close to the water. The third step, the methanol and the water, or the solute and the solvent, have to form attractive forces with each other. And that's what we're seeing here. The water's slightly negative end goes to the slightly positive end of the next molecule. And it keeps going. Sometimes it's water to water, sometimes it's water to methanol. But since the methanol has a slightly positive and a slightly negative end, it can make an attractive force with the water. And as a result, it will dissolve. Let's try another example. Sodium chloride in water. We already know sodium chloride dissolves in water. But why? First, sodium chloride is going to be a lattice structure, which is what we see here. In this case, ionic bonds are what's holding the ions together, and they need to break apart. Water also has attractive forces that break apart. Then what happens is that the ions are going to be attracted to the water molecules. So a negative end of a water molecule will be attracted to the positive ion of a sodium ion. Or the positive end of a water molecule is attracted to the negative ion. And this keeps going. Now, while we've given two examples of things that are polar covalent and ionic and show that they dissolve, that's not always going to be the case. Remember, it's a three-step process. We need to break the attractive forces in the solvent. We need to break the attractive forces in the solute. Then we need to form attractive forces from solvent to solute. This has to be a great enough change that it can overcome the energy required to do this. If this is not a big enough overall change, then it won't be worth it to the solvent and the solute to break apart. So for example, here we have methane, CH4, and water. And here we have our CH4. We have the C, and the blue spheres are the hydrogen. Now, these are all nonpolar molecules, and their main type of force that holds them together is London dispersion forces, which are caused by temporary dipoles when there's an unequal distribution of electrons. So there's not always going to be that slightly positive, slightly negative side. Water, though, has hydrogen bonding. It has a permanent dipole. It always has that positive, negative side. So it's going to take a great deal of energy to break up these hydrogen bonding. Not much energy to break up this. But then when water tries to attract one of the nonpolar molecules, there's nothing there. The water is much more likely to go back again with the original water than it is to go with the methane, because the methane doesn't have a permanent positive and negative side. The water does. So in this case, the attractive force from methane to water is not great enough to overcome the energy needed to break these attractive forces, and methane won't dissolve. So how can we remember what does dissolve and what doesn't? The general rule is called like dissolves like. And in this case, whenever you have a polar solvent, this is something that has a slightly negative and slightly positive end. It's going to dissolve other things that have a positive and negative end. These are things that are ionic, which have a clear plus and minus ion, and also other polar substances. Nonpolar solvents, which have Lennon dispersion forces as their predominant attractive force, will end up dissolving things that are also nonpolar. It's not a perfect rule, but it's a good predictor.